Swayam Prabha. Digital India. Educated India.
After learning the different types of stresses that may exist within a structure, for example, normal stresses, shear stresses, and bearing stresses, and so on, what we are going to do next are study different loading conditions, right? And then based on these loading conditions, what we are going to see is that what are the different types of stresses these loads induce within the structure. So today we are going to start on the new topic on axially loaded structure. What it essentially means that if I have a structure and this is the longitudinal axis of this particular pen which I am holding, and if I am applying the load pulling or pushing, right, these loads act along the longitudinal axis. So these are the axially loaded structures. So it acts along this particular axis, so hence the name axially loaded structures. Now you might be wondering that if I have a structure that is axially loaded, for example, the ones that you see over here, this load acts along the longitudinal axis, this acts along the longitudinal axis as well. You might probably be thinking that this is easy because this is only going to induce normal stresses. But through this chapter or through this topic, what we will see is that it really depends on which point of the material you're looking at or which point of the structure you're looking at and how you're looking at it, right? Now, analogically, the stretching and the contracting of these structures under these axial loads can be mimicked in terms of a spring over here. You have studied springs in your, +2 and the entrance examinations. So essentially, if you're pulling it, you will have the stretching of the spring or the contraction of the spring if you're pushing it, right? But always remember that the mechanism in which a spring stretches or a spring contracts is actually vastly different. For example, here in these ones, this load causes a direct stretching and a direct contraction, and the different smaller elements within this particular rod over here, or this one for this matter, undergo an expansion or contraction. As opposed to that, in springs, actually the loading mechanism and the load transfer is quite complicated. So this load essentially traverses through these coils of the spring. So the figure of the spring here is just as a demonstrative example. The truly axially loaded structures are structures which are of the kind of the ones that you have here, or practical examples of your building columns and so on, right? So now just getting into this particular topic. So first what we are going to look at are essentially prismatic bars. So remember, if you don't remember what prismatic bars are essentially the bars in which the cross section remains same along that particular length, right? So, and that cross section can be anything. That cross section can be it can be a solid cross section, circular, it can be a rectangular cross section, it can be a hollow cross section, and so on. So things which we are going to derive are valid for any kinds of cross section as long as the bar is prismatic. That means that this cross section is same across that particular length. For example, this pen is probably non-prismatic because here you have a shorter cross section, and towards this particular end you have a thicker cross section, you have a thinner cross section here. This is a non-prismatic member that you see over here. As opposed to that, this sponge is probably a prismatic section because all across it has the same area of cross section, right? Now, coming back to what we had actually studied until now, is that if we have a particular rod, something like this, and if you're pulling it with this particular force P over here, you will undergo some amount of deformation delta, right? Now, as you can understand, this is a clamped end over here. So as a consequence of this support being there, we will of course develop some reaction, right? And the magnitude of the reaction will also be equal to the applied loading P over here. Now, regardless, remember that what we had derived is that from the previous topic. So we have derived the expression for the stresses and the strains, right? And also we know that how stresses and strains are related, right? So if we take each of these one by one, what we have kind of learned is that my sigma is equal to P divided by A, right? This is for the stress. And for the strain, which is designated by the Greek symbol epsilon, we have epsilon equals to delta divided by L. We know these two quantities, right? And for within the proportionality limit, within that linear region where Hooke's law is still valid, what we know is the relationship between sigma and epsilon is that your sigma equals to E, the Young's modulus or modulus of elasticity, times epsilon over here, right? Now, if I do a little bit of rearranging, let's see what we get. So we can write sigma as P divided by A. This will be equal to the Young's modulus times delta divided by L, right? So this further gives me, if I do a little bit of rearranging, what I get is my deformation delta, which is essentially this particular quantity over here, becomes equals to P times L divided by A times E, right? So this is an extremely important relationship that you have, that delta is equal to PL divided by AE. You will use this particular formula through and through when you start to solve problems of structures under axial load, right? Now, in this particular expression that I wrote over here, you see the terminologies. You have the load P, right? You have the length L, right? And A, which is the area of cross section, and E is the Young's modulus of this particular material, or whatever the material this bar is made of, right? Now, just going ahead, and if we have to just write this formula again, what we have is what we just derived, what we just derived is delta equals to P times L divided by the area of cross section times the Young's modulus E, right? Now take a look at this formula, especially the denominator. There is a particular terminology for the denominator that we have over here, this particular guy, right? This guy is known as the axial rigidity, right? Why is it called axial rigidity? Let's just break up the words. Axial because you're dealing with axial loads, but why rigidity, right? Now if you take a look at this formula, right, for a bar for a given area and a given area of cross section A and the Young's modulus E, if you bump up the area, your deflection becomes smaller and smaller. And if for a particular material, if you take a different material with a higher E, then this delta also becomes smaller, right? So these terminologies, is A and E together, as it goes higher and higher, it makes the structure more and more rigid. Essentially, your deflection becomes lesser and lesser, right? So this particular guy over here, this is known as, these are just terminologies, this is known as axial rigidity, AE, right? Now, a couple of derivatives from this particular formula, which you will make use of maybe now or in some of your future courses. So if I take this particular formula again, and if I write it in a slightly different way, that your delta equals to L by AE times P over here, what it essentially means that if my P is equal to 1, right, if my applied load is equal to 1, the deformation I am going to get is L over AE, because it is L over AE times 1, right? So this quantity L over AE is nothing but deformation under unit load, right? And it's also known as flexibility. Designated by the symbol F, right? Now again, if I rearrange this a little bit and bring P to my left and the rest of the quantity to my right, what I essentially get is P, I'll write this again, I get P equal to AE divided by L times delta, right? Now similar to between these two is that how we expressed when P equals to 1, what is the delta here. When delta equals to 1, your P is AE divided by L. So what does it essentially mean? That means that this is the load, AE divided by L is the load to produce unit deflection, right? So if I have to write it, so this is the load for unit deflection, and this is known as stiffness. K. Right. So as you can tell that K is equals to 1 divided by F, right? So essentially stiffness is inverse of the flexibility, right? In real life as well, if someone is flexible, that means a stiff person, you know, has an opposite nature compared to someone who is flexible, right? So this is also kind of an important relationship later in your even in this course or some of your future courses, that you will see that, you know, these relationships pop up. For example, when you do structural analysis or structural mechanics, you will see there is a flexibility method and stiffness method which uses some of these kinds of formulations which are there, right? So now that we have the basic groundwork done, for example, this particular guy over here, right, that delta is equals to PL divided by AE, let's look at one example of how we are going to make use of this particular formula to solve a particular problem. So now that we have just started to scratch the surface of this particular topic on axially loaded members, and you have learned the formula that the deflection delta equals to PL divided by AE, you are probably wondering that at most a complicated problem that I can give you is just a rod maybe fixed at one end, and if you're pulling with a, you know, load P, and if I give you the length of the rod, the area of cross section, the material it is made of to help you calculate the E, right? And eventually I will ask you just to calculate the delta, the deflection. Well, we'll look at a slightly more involved problem than this simplified example that I was talking to you about, right? So this is the example problem that you have. Now, before we go ahead and look into this problem and see what it asks us to do, I want you to inculcate this habit that whenever you get a problem, whether in the exam or while you are solving practice problems, right, you know, don't be taken completely by surprise just by the looks of the problem. First, try to understand the system. You know, every complex system, every complex problem can be broken out into smaller, simpler chunks. And once you start to understand or start to have at least an appreciation for those, the more complicated ensemble of these smaller chunks, it gets much easier to solve. Now let's come back to this problem at hand that we have over here. And as I said, first let's just try to understand the system. So what you have is a rigid member ABC. It is mentioned it is rigid. So rigid meaning that it cannot bend, it cannot have any deformation or anything. It's just, you know, one very strong member that is there. It can maybe at most, if this is the member, it can maybe at most move in plane. You cannot have any bending or any other kind of deformation that is there. So you have a rigid member which is supported by two members over here. You have one member BD, right, which is clamped at the end, and you have a pin over here at the top at the point B, and another member CE, which is, you know, pinned over here, and you have a pin over here as well at the point C, right? And at the for this member ABC at the end A, you're pulling it down with a force P over here, and some dimensions are marked. This is 452.25. This CE is 600 mm, and this distance between D to E is 120. So that will help you calculate the length of this bar BD, which is going to be 600 minus 120, that is 480 mm over here. Right, now let's see what are we given and what the problem asks us to do. So we are given the magnitude of this particular load P over here, 23.2 kilonewton. Then we are given the cross-sectional area of AB of this bar BD and the cross-sectional area of this bar C. It may be circular, maybe square, we are not clear, but anyway, as long as the cross section is given, we are fine with it, right? Also, while the problem asks us to calculate the delta BD, the deflection of this or the shortening or, you know, elongation, we'll see what it is, and the delta CE and the vertical deflection at A, right? So now that you see this system, now try to visualize that how the system would behave, right, when you are pulling it with this particular force P. Now, when you're pulling with this particular force P, of course, this point A is to will go down over here. Now we have to figure out that what happens to this point B and this point C over here, right? Whether they go up or whether they go down, and the amount of which it goes up or it goes down is delta BD and delta CE, right? So maybe just hypothetically, let's start the problem by just drawing the deformed configuration, and given that the bar is rigid, probably the deformed configuration or the deformed shape of this bar will be maybe something like this. The point A definitely goes down over here, so maybe you will have something like this. I will draw a sort of an exaggerated deformed shape so that you understand, right? So maybe it happens something like this. Right? So what was my point A before over here? Now it has, say, moved down to this particular point. I am going to call this point, say, A prime. Right? What was B has maybe moved to somewhere over here, so this is my B prime. C was over here, C has now moved up, so this is C prime over here, and the end is also slightly lifted, right? Okay, so this delta BD, which the problem asks to calculate, is the deformation of this, bar, that BD that you have over here, which is essentially this particular distance. So let me mark this particular distance. So this is my delta BD, right? Similarly, the point C has moved up over here. So, this particular distance that I have, this is my delta CE, right? So we are supposed to find this delta BD and this delta CE, and the problem also asks you to find the vertical deflection at the point A, which is maybe this one. So if I have to, join these 2 points by marking this dimension over here, this is nothing but your delta A, right? So we have to find these 3 quantities, right? So now that you have sort of figured out how the deflected shape looks like, you can think about how the forces in the members BD and CE will happen, right? So you see this BD over here, the point B moves down, so the particular bar, BD is undergoing a compression, right? So the forces in the member BD are going to be compressive forces, right? Okay. Now what about the member CE? The member CE, this point C moves up, right? So that member CE undergoes an elongation. So that means that the member CE must be in tension, right? So now if we have to draw the free body diagram of this ABC over here, and the whole reason for doing that, see, ultimately you have to find this deflection. So for example, if I have to find this deflection delta BD over here, just as an example, if I have to write that, delta BD, is nothing but equals to F times FBD, that is the force in the member BD, right, divided by the area of BD times the E of this particular material, that is the E of BD. Now this problem statement doesn't specify the E, so maybe let me just write it over here, that along with this information you're also given E is steel, this is a steel bar, 205 gigapascal GPa, right? Okay, so this is how we find the deflection. So you see your area is known, right? Your E is known, so we have to find what is the force in this particular member, and we know that the force in this member BD is compressive, right? So the force on this particular rigid bar, this ABC that you have, must be pointing vertically up, because this bar BD is getting pulled down, so at the same time the force this member must be experiencing, the ABC must be experiencing, is going to be vertically up, right? Similarly, this member CE over here is undergoing an expansion, and this bar ABC is trying to keep it at the same place, so the force at the point C will be pointing vertically down, right? So and also in addition to that, remember, are there going to be any horizontal forces in either of these points C and E? Well, in this member CE there cannot be any horizontal force, because the point E is pinned, right? If I put any horizontal force, it will constitute a system, so your things will fail, so you'll only have a vertical force which is going to act over here, right? But at the for the member BD, the point D is clamped over here, so that can take some amount of horizontal force. But from the from the system of forces that you have, since your that force P, it points vertically down, you're essentially not going to have any horizontal force in the system. But just for clarity and just to mark it out, what do we see if we draw the free body diagram of this ABC? Remember what we decided, or what we figured out, that for the member ABC at the point B, since this point B is undergoing down, it is going to apply a push up at the point B over here, and since this point C is going up, for the bar ABC at the point C, the force is going to point vertically down, right? So this is your the free body diagram of the ABC that you have, right? So you have this force P over here, you have this FBD, this one, remember this point B was going vertically down, so as a result of which it is going to push against that particular bar ABC, and this particular force goes vertically down, right? So now if you remember from the last page, what we need to find is this FBD for this member BD to calculate the deflection. Similarly, for this CE to calculate delta CE, what we need to find is what is the force acting on this particular member, right? So let's go to the free body diagram again. So you have this P over here, and remember this horizontal force which can exist, but in this case you are simply going to have H equals to 0 from your summation of Fx equals to 0. So if I have to maybe just write it out over here, that from summation of f of x equals to 0, that gives my H as equals to 0, right? And if you see these ones over here, so how do I determine FBD and FC? Very simple, from the equations of equilibrium in the y direction, and also by taking the moment about the point A, right? So from using these two relationships, that summation of your Fy must be equals to 0, and summation of the moments about a particular point, say A in this particular case, right, is equals to 0. So these two relationships will, if you solve it, it will give you your forces, that is FBD comes out to be 3 times P, right? I'm not substituting the value of P, I can do that at the very end, and then also it gives you F of CE, right? It comes out as 2P. Right? Now, does it sort of make sense? Because it says my FCE is 2P, which is going vertically down, right? I am marked the forces in the right direction, so I need not put a negative or the positive sign. If after solving you see one of them comes out as negative, that means your force should be marked in the other direction. So these things you can figure it out, right? And FBD, it comes out as 3P, right? So this is 3P, right? So in some way it makes sense, because if you see this FBD over here, 3P, 2P, so in between these two you have a force P which is going vertically up, which is balanced by which balances this applied force P over here, right? So now that we have this 2P and 3P, what we have to find are the deflections over here, and the deflection of the point A. Now again, going back to the deflected shape, I have a better figure for you over here. So this is how the deflected shape looks like. Remember, this is what we drew in the first page over here. So A goes to A prime, B goes to slightly down B prime, and where the deflection is this delta BD, and C goes up. So this is the delta CE that you have over here, right? So, and also what we have already figured out from our last page was that FCE is equal to 2P and FBD equals to 3P. Right? Now all that remains is to find these deflections. So let's start to calculate them, right? So you have the delta BD as equals to F times BD divided by the area of BD times the E I noted already. I will write here once again that given your E is also 205 gigapascal, right? Now if you substitute these values over here, that is your FBD comes out to be this particular quantity over here, that is 3P. Oh, sorry, there will be a times L, PL by AE, remember? So it will be FBD times the length of BD, which is this particular quantity over here, which is 600 minus 120 is 480. So times 480 mm divided by the area of BD, which is given 1020, times the E, which is 205. So you have to take care of the units and so on, whatever goes into solving this one. So if you put these things in place, and then P, remember P is also given as this particular 23.2 kilonewton or 23200 newton, that is 23200 newton. So this delta BD comes out to be around 0.16 mm. Right? Now, in a similar way, if you try to calculate the delta CE, and remember that this delta BD, the point B actually goes vertically down. So this is actually a compression which is happening. So maybe we just write it. Right? So in a similar way that we have our delta CE, you can calculate similarly FCE times length of CE, which is 600, divided by the area of CE times the E. The E is the same for both, and again if you substitute the numbers over here, for example FCE is 2 times P, where P is 23200 newton, what you will get that this particular quantity comes out to be 0.26. I have already solved this problem. Right? So I'm not doing the inner calculations that are there. Now, something to appreciate here, right? You see these numbers, 0.16 mm. How much is it? It's very small. For example, the scale I have over here, this is 15 centimeter. So 0.16, that to 0.16 mm. So you can imagine that how tiny these deflections are. And that's actually quite logical, because you want to keep things within the elastic limit so that you are not inducing failure for these small deflections, right? You are still within the elastic limit and you do not have permanent deformations and so on. So for example, if you have this bottle over here, right, and if I apply force in the longitudinal direction, that is a pure axial force I'm applying over here, you do not see this bottle getting squished, but let me assure you that there are actually tiny deflections, deformations which are happening, and the moment I'm releasing the load, the bottle comes back to the original configuration. You put some strain gauges and you can measure, you will see that very small deformations actually happen. Right? Okay, so our job is not completely done yet over here, because we have calculated these two quantities over here. So we have calculated delta BD, delta CE. Now we also need to calculate this particular quantity, which is delta A, which is this guy over here, delta A. Now how do we do that, right? So it can be simply done using similar triangles. So if you see over here, right, what I have done over here is that this point A, I have drawn a parallel line which is A double prime, B double prime, C double prime, which is parallel to this one over here, where C prime, not C double prime. This is where the final point C goes, vertically up over here. So if you simply use the similar triangles which you have over here, that is, if I do so let me just maybe write it out so that it's clear. So if I take A prime, A double prime, that is this particular dimension, right, divided by this length, that is A double prime, C prime, this is going to be, what is the similar triangle to the bigger triangle, the smaller one over here. So this is going to be equal to B prime, B double prime, right, divided by B double prime, C prime, right? So this length divided by this one must be equal to this length divided by this particular one that you see over here, right? So now if you just expand these quantities, this particular term, this A prime, A double prime, is nothing but delta A plus this value of delta CE that you get over here. So if I just expand this one, this is delta A. Remember, delta is the one which we're trying to calculate, delta CE which we have already calculated, plus delta CE divided by this entire length A double prime, C prime, which is 450 plus 255. So divided by 450 plus 225, right, must be equals to your B prime, B double prime. If you take a look at B prime, B double prime, that is delta BD plus delta CE divided by this length 2 25. Right now, you must remember one particular thing. Although that this is, in compression and ideally should have a negative sign if you're not writing the word compression like I have done over here, and this one is in tension, this 0.26. So let me write that here as well. So this is actually in tension, right? So expansion or compression, or maybe not tension. We should probably write as, since I have written compression in the other one, it should be expansion. Right, so although it's a compression and expansion, so one is a negative, one is the positive. We typically take the tensile forces, tensile stresses, and corresponding the extension as a positive quantity. But when you are using the similar triangle, you just deal with the magnitudes. There's no positive and negative sign, all that, because what you're doing over here is pure geometry, nothing else, right? So all these quantities are going to be positive because you're just dealing with triangles. Forget about deformations, which one is having a compression, which one is having a expansion, right? So in this particular equation that I just wrote over here, you see all of the quantities are known. For example, here delta CE, delta BD, delta CE again over here. So the only quantity which is remaining is this particular quantity, and if you solve it over here, what you would get is that your delta A will come out as 1 mm. Right? So these are the answers that we have over here. So we were asked to calculate what is my delta BD, which I have calculated here, delta CE, which we have calculated over here, and delta A eventually, which we have calculated over here, right? So I hope that this particular example made some sense to you into understanding that how bars which are undergoing this uniform compression, how they compress, or how they expand if it's undergoing a tension, right? But in this particular example, you saw that the entire length of your bar, for example the BD and the CE which we saw, it is just undergoing one force. There are no intermediate forces which are there. So the next topic which we are going to cover, or the next subtopic rather, it is going to deal with prismatic bars under non-uniform loading. So instead of having just one load at the very end, or just one load transmitting throughout that particular member, you are going to have a member where you will have one load here, maybe another different kind of an axial load here. So it becomes tricky that what is going to be the final deformation of this particular bar over here. So that comes as our next topic.